So I'm here today in Yorkshire to speak with Chris Starr, who's very generously given us a bit of his time. And Chris was working for the RAF and did a lot of work for the restoration of the Messerschmitt 109G, known as Black 6, which you can see a painting of behind Chris. Chris, I don't know, maybe you can just start by telling us a little bit about your background and how you got involved with restoring the engine of Black 6.
Yeah, thanks, Callum. I was fortunate to discover, as it were, the restoration of Black 6 going on at Benson in about 1989. That time I was flying the Tornado with the Air Force, and as an ex-apprentice and qualified on aero engine servicing and aircraft servicing before that, I was very keen to be interested in historical aircraft. And having discovered that this aircraft, Black 6, was there, I introduced myself to Russ Snadden, who was the leader of that restoration, which started in 1972. And by that stage he had all the elements of a rebuilt 109G coming together in the hangar. So it was a very interesting time for that particular project, and I was pleased that Russ was keen to have some assistance, and that's how he had sponsored, basically, if that's the right word, the restoration. It was voluntary. Although the aircraft was owned by the Air Force, and Russ had been in the Air Force originally, the work was done without financial support, so by volunteers and industry as well. Rolls-Royce Bristol particularly, and a host of other companies helped with minor parts over the years. So as I said, in 1989 he had a nice corner of the Wessex major servicing hangar to work in, with the aircraft components coming together. And initially I was a bit of a newcomer to the team, with quite a few engineers. Probably about 4 of the Benson engineers were regulars at the time, working on Sundays. So I was driving down from Marham to Benson early in the morning to crack on and do about 8 hours on the project on a Sunday when I was available. Exactly where I fitted into the picture only gelled as the project, or my involvement with the project, went forward. The complexities of the 109 are maybe a little bit surprising. Russ Snadden said himself that he started the project with a small aeroplane on the basis that small aeroplane, not too much work, probably a good one to cut his teeth on for aircraft restoration. But it's like most fighters, it's a dense machine, and there is a lot of engine and systems packed into that sleek skin of a fighting machine, that once you start really taking it to bits to make it work again, it becomes apparent that it is complex and dense, highly compressed mechanical systems into a small space, and that means it's a lot of work and complexity to restore and make functional. So yes, to be honest, the engine holds the mystery, and it's an iconic engine. At that time, late 80s, there were only a couple working in Germany where they were re-engined, MBB re-engined a Hispano Bouchon with a 605, and that was about the only working 605 in the world at the time, so a very rare machine.
So what was the first engine system or component that you had to make some dealings with?
That's interesting, because the engine was returned from Bristol, Rolls-Royce Bristol, as a complete bare engine, and the first real work on the engine was to install it in the airframe, to be honest, and that in itself is complicated. If you were working on aircraft, if you're qualified on a type, then you know all the ins and outs of a particular aircraft, and you know all the equipment that's used to service it and repair it. But when you're working with something like a 109, where the team were either adapting ordinary equipment to work on the aircraft and the engine, or having special equipment made to help assemble the aircraft, then it was an interesting time in itself just to fit the engine. Now the 109 is really well designed for easy engine installation and removal. However, as I've just described, when you're doing it for the first time, it isn't straightforward. The engine bearers are individually adjusted with screw thread adjusters so that the engine sits at the correct angles in the airframe, and just understanding exactly how that should be and adjusted for the aircraft to fit properly is one element of fitting. And I do remember that there was quite a lot of time spent looking at the diagrams, assessing what angles the engine should be at relative to the airframe, and the adjustment of the engine bearers to get it at the correct position took quite a lot of time. And then, great, fantastic, the engine is hanging there in the airframe correctly in the bearers, but it's just a bare engine. And on the 109, the rest of the cowlings and the pipe work and the propeller have all got to be built onto the bare engine once it's assembled. So a lot of work went on after the bare engine was installed in making pipes that had been lost over the decades. If you look at a Spitfire, the cowlings are held on by many Zeus fasteners on the panels that fit onto the structure which is on the engine bearers of the Spitfire. On the ME 109 you've basically got big aluminium bearers that the engine hangs from, and the cowlings are only in three pieces: the complete lower cowling with the oil cooler, and the two side cowlings which open up like wings on the hinge along the top line. Now those mount very simply onto the engine, basically because the exhaust stubs hold on troughs either side which keep the exhaust gases from going under the cowling, and those steel construction troughs mount those three big cowls that simply fasten on with quick release fasteners, and the cowling is held on the 109 in that way by the exhausts, as it were. So it's a very accessible engine once you've got it built up, but as I say, it's a big job. Once you've hung the engine, you've then if it's a bare engine that you're working with here, you've then got to build on the other structure that goes underneath to hold the cowlings on with all the pipes underneath. So that was a long job after the initial fit of the engine onto the basic airframe.
So with regards to what's typically regarded as the most tricky system of the engine, which is of course the injection system, how did you first go about finding the information and learning about how the system worked and functioned and should be set up?
Yes, that's a good question. There we go, there's a DB fuel injection pump just sitting there. How does it work? Russ Snadden had accumulated a collection of the manuals for the aircraft in various languages: German, Swedish and Finnish, from other operators of the 109, and he had translations done by Rolls-Royce Bristol, and they'd done a lot of that because they did the strip and rebuild of the engine for Black 6. So in that information was the description of how the fuel injection system worked, and there was no better way than to read those translations and the original manuals. Although I understand some technical German, I'm not a fluent German speaker, or I then had to read the translations for the real gist of what was being told in the manuals. A lot of the information is numbers and figures and graphs, and then you can extract what you need to know from that, but the translations were invaluable, so that's how we discovered how the system worked. Very different to the later Allied fuel injection systems, because the the Mercedes Bosch looks like a diesel pump. It was developed from the direct injection diesel pumps. That system is complicated, complex. The British systems or Allied systems, American, Bendix, some of the SU later fuel injection systems worked generally with a single point fuel injection into the supercharger, whereas Mercedes Bosch designed it to be direct into the cylinder. It's complicated, it's technical, and when you get into it, it's very detailed, but it's not impossible to understand. It was a matter of applying yourself to reading and understanding through that reading how it worked. The fuel comes along to the injection pump from the backing fuel pump, and it's delivered to a deaerator, which is really just a float in a fuel chamber, and as the aircraft changes position, the float is weighted at the bottom and it moves around to keep the air at the top, and there is a system with a hole at the top which allows air trapped from the fuel that's risen to the top to flow out of another pipe, and it goes back to the fuel tank. So this was the Bosch method of, it's a German Entlüfter, so it's a air extractor deaerator, which in pitch this will swing around, and whichever attitude it's in, it will take the bubbles out of the, if there are bubbles in there, because air trapped in the fuel will affect the actual quality of the pumping action of the fuel pump. So this is one of the items that's integral with the fuel pump, which Rolls-Royce had overhauled, and it's quite a technical piece, complicated technical piece. The V12 has blade and fork connecting rods, and this is the setup out of the DB605. This is a set. As you can see, this is the big end, and this is the plain bearing that goes on the big end journal of the crankshaft. The blade rod that you can see in the middle there has got a similar plain bearing underneath it, which is all lubricated by oil in this engine that comes up through the crankshaft and then out into the from the journal into this plain bearing, and there are holes inside this bearing to get it out onto the plain rod. But this is getting on for sort of 15-20 pound weight, which is considerable. It is a big engine, it's 36 litres, so that's why these things are as big and heavy as they are. And again, this being plain bearing, similar to a Merlin or a Griffon, the earlier DB601 had this big end journal with roller bearings in it, which changed two plain bearings for the 605. So it was an advancement. It did give them some problems with the 605, getting the technology of their plain bearings, Mercedes getting the technology with the plain bearings up to speed, but it's very similar in design concept to virtually all the V12s.
And I suppose you must probably remember the first moment that the engine ran with the Black 6 restoration.
Yes. Very interesting days. In 1990 we were working towards engine running, having fitted it in the YO9, dressed the engine with all its pipes, oil tank, fuel pipes, air pipes, ventilation. I think it was 17th of March 1990, on the top of my head, something like that. The engine started with Roger Slade from Rolls Bristol in the cockpit at the time, and ran for the first time since its overhaul. That was a big day. We'd been trying for quite a few days to start it, and when it did go, it was very exciting.
And obviously the fuels that were in use in wartime are no longer available. But for the fuel for Black 6, was this would have been in wartime the set up with B4 fuel? Is that correct?
Yes. So it was a roughly 87 octane B4 German standard fuel. Today we operate a Black 6 on 100 low lead, so it's 100 octane low lead fuel, which is by definition it's a better resistance to detonation fuel. It's a very good fuel for the engines of today that run on it, and it was a very good fuel to operate a DB605A. The quality's high, and it's a higher specification fuel than the engine actually needs, so there aren't really any drawbacks whatsoever to the use of 100 low lead fuel, which is the modern general aviation fuel, and used by almost exclusively by warbirds, apart from racing, American air racing engines that run on exotic fuels. And it's there's no compatibility issues whatsoever with the DB605 on using that fuel.
Who actually flew the plane for the first time? Can you remember?
Yes, it was Reg Hallam, Group Captain Reg Hallam, and he flew Black 6, having been invited through Russ Snadden and the Historic Aircraft Committee that were responsible for the airframe at the time. And Reg Hallam was an experienced operator, very nice chap, who came along and learnt all about operating this strange beast and was very keen to fly it.
So can you remember any of the initial impressions that Reg had after his first few tentative flights in the plane?
Reg only made the one flight in the aircraft, and his first impression I heard over the radio, Russ Snadden had a mobile radio there, was it goes like a train, Russ. After flying around a little bit, the weather was terrible, and he was very pleased with it. He had nothing but praise really for the. I think he realised what a historical aircraft it was, and he was very, very happy. Unfortunately, the takeoff, it had a problem with some loose turf, which had raised the tail a little too high and cut through some turf with the propeller, which bent the blade slightly. But he didn't know that in flight, and it was only after he returned that we could see that the tips were bent forward, and that was another issue that required resolving.
I imagine the blades could be repaired skillfully from that kind of event.
Yes, they were there with the aluminium blades original. Depending on the sharpness of the bend, they either need heat treatment or not heat treatment. They can be cold bent or not, and but it's done by specialists, and Russ had to get that sorted out. Subsequently, we were fortunate to get some composite blades which were made in Germany, same profile as the original, same shape, but they were better because in as much as they, if you have a prop strike and say if you have to do a belly landing, then the blades break much more easily than the aluminium, and there's less likelihood of less damage to the engine. Lots of people will be aware that German engines were a lot of talk of power boosting. Of course, British engines had power boosting. Merlin's had nitrous oxide injection on some Merlins for, I think it was Mosquito fighter operations. But the Germans in the latter part of the war particularly used nitrous oxide and for high altitude boosting, and water methanol for running higher boost pressures. You spoke about fuel earlier, B4 relatively low octane, and even their C3 relatively higher octane fuel wasn't really in the same league as the Allied fuels when they went to 100-150 octane late war. So one way around this is to use water methanol, and the injection of the water methanol is quite simple in the German system, straight into the eye of the supercharger from a tank, and all you need to do there is pressurise the tank with air pressure, and when you open the valve, the water flows through the graduated nozzle into the eye of the supercharger. Makes that water methanol prevents the detonation at higher boost pressures, manifold pressures, and you get more power from the engine. So this valve, this is a genuine item, is a simple solenoid valve, and that's all you need to. You can see the connections on the end of the valve to switch the water methanol on and off. To help the pilot, there was a gauge, just showed you the pressure, because without the pressure the water methanol doesn't flow, and if it stops flowing then the engine operating at too high a boost pressure can be damaged. So they had the pressure gauge to show that the pressure was there to push the water methanol, had the valve here, genuine item, to let it go through when the switches were made.
So how does the pilot actually arm the system and turn it on?
Well, Germans made it on the 109, everything was simple. The solenoid valve's electrical, and there was a main switch for energising the system, which would put the power through into the circuit when he wanted to be enable the master switch for the water methanol. So that's that. And it's based on the boost pressure of the engine, and this is a micro switch which was operated by the movement of the throttle, which had a metal trigger or a trip on it, which would press as the throttle was moved high enough to get the boost pressure high for the water methanol. It just depresses the plunger on this switch, which again completed the electrical circuit to the valve. So pilot turned the basic system on. This micro switch activates when the throttle is open to the 110% position, and that opens the solenoid valve. So it's a simple system. Really, from my perspective, I think the Germans were pretty much stuck with their boost pressures until 1944, May 1944, when they introduced the water methanol. The British, particularly if you consider Merlin development, after 100 octane fuel came in relatively early in the war, late Battle of Britain, and the Germans really never got past 100 octane equivalent. But the British side then went on to up to 150 octane eventually, and Merlin was boosted. The boost pressure was increased right up to 30 psi of boost pressure. The Germans were stuck with their lower grade fuel, lower rated fuel, and they were only able to get their boost pressure increased when the water methanol injection came along in May 1944, effectively for operational use. As you can imagine, they Rolls-Bristol weren't able to sort of source a lot of spares, and in the late 80s, obtaining things like Second World War spare parts was, if anything, more difficult than it is today with the internet, and people more willing to sell items that they dig up from who knows where. So the early 605 DB605A engine, which was in Black 6, used a relatively early German spark plug, and this is one of them. It's a Bosch spark plug. I don't know how close you can see the electrodes, but it uses a fairly small steel electrode, probably a nickel steel electrode, with simple steel earth electrodes too, one either side of the centre electrode. that is a straightforward plug, not a really high spec plug. The best that can be said about it perhaps is that it's got a try and think of the ceramic insulator core, which was relatively modern for these spark plugs. The British had certainly hung on to mica, I think, for spark plug cores for insulators for a long time. Now, the Germans eventually managed to increase their boost pressures, and they did that primarily by introducing water methanol. And they found a lot of difficulties with these small electrodes on the spark plugs from simple materials being melted or eroded rapidly. And I don't know if you can tell me if you can see the electrodes on this. This is a late plug. This is a 1.8 atmosphere boost pressure ET10 plug, Bosch, which has a much larger centre electrode because the materials are still the same. There's still probably steel, nickel steel centre electrode and probably relatively simple steel side electrodes. And to the higher boost pressures with much higher heat loadings on the plugs, then they had to increase the size of the electrodes. I believe the real reason they're to take away the heat from the in the higher temperature combustion with the higher pressures, and that's part of the development in their spark plugs. Now, if you look at a Rolls-Royce Merlin plug at the same period, you'll find that it has a very fine centre electrode and two very small bars coming in from the sides for earth electrodes, made of precious metal and probably platinum and various other alloys, fine wire alloys, whereas this is a large mass, as in mass of the centre electrode type plug. Those allied plugs, the allied plugs had become these fine high value metal electrode type plugs relatively early on in the war, but the Germans were stuck with them probably through material difficulties getting the high grade materials, and secondly possibly simply because they weren't able to develop the technology at that time with their spark plugs. I think with the amount of aircraft being shot down over Germany, that their research institutes will have seen the Allied plugs, the same as they'll have seen the developments in all the engines from Allied aircraft. But that didn't mean they were necessarily able to convert that into modifications of their own equipment, because if they didn't have the raw materials or the actual production technology, they couldn't necessarily utilise it. I've been fortunate to be involved with quite a few engines, German engines, wartime engines, and you can see, especially when you get inside the engine, looking at the rotating components, and you see the quality did reduce after about 1942. Up until that point, internally you'd see beautifully polished parts of the internal parts of the engine, which the polishing is primarily to remove stress raising defects in the surface finish. But you can see that is degraded after 1942, with obviously less time being spent on the finishing of steel components. Also castings, so the large crankcase castings are internally finished after they've been cast as a huge 200 kilogram lump. Then, although they aim for the minimum of machining, internally they do have to work clearances on critical parts of the casting, and you can see that work, which will be beautifully done on an early engine, as beautiful inside as it is outside. You can see that goes downhill, and the cleaning work and the clearing work internally is done to a much lower standard. It's rough, so they'll use a much coarser mechanical means of removing the material, and leave it rougher than they would have done earlier in the war. And that's just to see. Obviously the material specifications would be varied. the steel's got to be strong enough for the component to function. But components that were less important, like even screws and nuts, you can again see that surprisingly here, if you're dismantling a crashed engine, which you have to use mechanical means to get apart, as in hacksawing them apart, you can soon see on a late engine that things like studs, small studs and less consequential parts of the engine can be much more easily cut, because the steel is obviously to a lower quality, and even the amount it's been corroded in the 80 odd years since it was made is obvious to you when you're working with these things. So yeah, that was obviously a factor for the Germans. After the aircraft went to Duxford and was operated there, the help from Rolls-Bristol had really finished with the return of the engine, and after the initial problems were sorted out, Roger Slade, who lived in Bristol, wasn't able to really come and do any more work on the aircraft after 1991 at Duxford. So then I really got more involved with looking after the engine and became the primary person when it came to the engine aspects. So I didn't install myself into that post, I suppose. That work included considerable manpower effort over the years. We had the engine virtually completely apart for a year when the starter drive adapter on the rear of the crankshaft cracked, and to replace that required the whole of the rear ancillary case removal off the engine, which takes off everything: the supercharger, all the drive ancillary case with the magneto, the pumps, even the fuel injection pump underneath comes off, and that was a hell of a lot of work. At the same time, we had the cylinder banks off to replace the piston rings, because we had a drop in compression on several cylinders, and so the cylinder banks came off as well. We had the engine down to the basic crankcase in the workshop that we had at Duxford. Putting that back together and it working and getting the engine back in recommissioned after such deep work was very rewarding to me, and that's apart from the Rolls at Bristol work, which also included the crankshaft being out. That was what I did and the rest of the team helping me on that rebuild for that problem with the starter clutch drive and the piston rings was deep work and very rewarding. Ultimately, every flight was rewarding, because it's a dangerous aircraft, the 109, even when you operate it as safely as possible. So it's exciting every time you fire it up or a pilot goes and flies it. And once it's up in the air, you're thinking, well, let's hope it comes down and lands it safely. And so many companies helped out. It's impossible to list them. Russ does a good job in his book, which is worth digging out a copy if anybody hasn't read it. And you can find it, I'm sure, on eBay, or it might even be available from certain sellers new still. And to round off talking about that aspect, perhaps in a way, companies were willing to help when they understood what the project was, and the cachet of being a volunteer team effectively, albeit, as I've said, there was some financial involvement with Imperial War Museum, but the essentials of it were voluntary. Yeah. This is a Bosch PZ12 fuel injection pump used on the DB605, pretty much in this type, the 603, and the main elements of the pump, well, it's pretty obvious. These are the pumping elements in the top, which the fuel flows from to the individual cylinders of the engine. And if you realise that each element here is a little piston in there with a cam at the bottom, and as the cam turns it pumps the fuel out of the top through the pipes to the cylinder for the combustion. So it's very similar to the diesel pumps that were used by a lot of lorries and cars right from the early days of diesel engines. It's called a rack pump because operating these cylinders is a cam at the bottom, but on the other side there is a long gear, straight gear on a steel, it's called a rack, which can turn those elements to vary the output of fuel from each. So we've got fuel which comes in, we saw earlier, the deaerator, up through the big pipe into the elements to be pumped to the engine. But we've got to vary that by the use of the rack to match the engine's power output. So at low power there's very little fuel in each spurt, and at high power then quite a big slug of fuel, comparatively speaking. Now on a diesel engine it's fairly easy, a straightforward diesel engine, it's fairly easy because of the accelerator on a diesel, simple old diesel lorry, just goes basically to the rack, and it basically just alters the output from these elements with the movement of the throttle. But this is an aeroplane engine that can fly in a wide variety of temperatures, altitudes, and inlet pressures with boost with the supercharger. And so to control the movement of the rack, which controls how much fuel comes at each squirt, the whole of this housing at the left hand side of the engine here is the control element of the pump. The way it controls is just to measure the airflow, the air flowing into the engine by the pressure of it and the temperature. The speed on the drive at the far end is an input that's mechanical, and so therefore this drive here, the speed of the engine is taken care of mechanically because it's directly linked to the turning of the engine. So pressure inside this housing, it looks like this, and basically there is a diaphragm in the middle, and at one side is the pressure of the air in the boost manifold of the engine to the inlet valves, and the other side is the ambient air from the inlet before the supercharger. And I might be able to demonstrate, you see the springs in it, I might be able to demonstrate that according to the balance, here we go, according to the balance of the air pressures after the supercharger and before the supercharger, then the diaphragm forces the movement of the piston basically in the middle against the springs. Now that movement is picked up by a fork which fits into this part of the piston, which is an elongated piston, and this fork extends downwards into the body. Inside the body we've got more capsules and a lot of oil. The oil lubricates the components. There is an integral oil pump which is again driven after coming all the way along with the cam at the bottom into the body of the mixture controller. To move the rack, which is controlling how much fuel is injected, takes quite a lot of force. This has got strong springs, but it's only working on a little bit of air pressure. It's only a few pounds. To move the rack takes probably tens of pounds to move it effectively. So also inside the mixture control is a oil pressure operated power amplifier, which simply uses a very small valve which is operated by the forces that this generates through the yoke down into the body, moving a spill valve, which then goes into a larger hydraulic piston to move the rack, which adjusts all the pumping elements. So great, we've got correction so far for the speed of the engine directly. We've got air pressure, the boost pressure of the engine, the ambient pressure on the other side. Around the other side of the pump, we have another selection of adjustments. Before the power amplifier is actually operated, it's worked upon by the temperature of the air, which is put onto the mechanism here, mechanical mechanism here, and moves this rod, which swings the lever you can see at the far end to influence according to the air temperature of the air that's being inducted into the engine. And this is the sensor which is doing that work. There's a temperature, fluid filled temperature capsule operating a linkage which is finely calibrated with a rod which runs, this is actually broken off, there's a ball that fastens on the end here, and as the temperature of the air being compressed in the engine by the supercharger increases, this lever moves appropriately, which is imposed through a rod onto this lever, which moves these levers, and it's not doing anything at the moment, it doesn't want to move very far. So there are your corrections. Engine drive speed, boost pressure and ambient pressure, down into the gubbins of the mixture controller, superimposed with the temperature of the air coming in from the supercharger into the power amplifier to move the rack. It's quite a complicated thing. If you get it apart, it is the proverbial Swiss watch. You can imagine that the complex mechanical parts are matched by the mathematics of the things that you are mixing together here. The effects are being mixed mechanically to work out how much fuel you should get because of the movement by the rod. In your digital engine control in your modern car, those things are all done in a digital computer. This is a mechanical computer that takes these inputs. This sort of thing was called a commander-garat on the BMW 801, which did the same work. It used the engine speed, the boost pressure, ambient pressure and the temperature to work out the fuel required by the engine. But on the BMW 801, for some reason that functionality was given this great claim of commander-garat. On the DB605, the fuel injection pump does that in the mixture controller and does all that work within the one unit, but it's just called the fuel injection and spritzer pump. UMO 213 is a fuel injected engine, and that also had a slightly similar system of mixture control, but again it was remote from the fuel. The pump was effectively just this bit, and the mixture control management was done in the separate part of the engine subsystem. So there was a rod coming from that to the injection pump to transmit the demand for fuel. Reliability of this is very good. It's more complex in some ways than it's certainly a lot more complex than, say, an SU carburetor on the early Spitfires, which is a simple. It doesn't look like the SU carburetor on a Mini, of course. It's Skinner's Union is what the SU stands for, which is the company. But the SU on a early Merlin is a simple twin Venturi carburetor. With a lot less parts, and mechanically it's more complicated than probably any of the most of the Allied fuel systems that went onto their aero engines in the Second World War. But I think it's quite effective. Yes, effective. It was effective. It worked properly. It gave great throttle response. Good fuel economy. It's self-contained. The only things it needs are those inputs that I've described for the temperature, pressures, and the drive from the engine. It does have a separate feed of oil for its lubrication, which is just plugged into the engine oil circuit. There is no link to the pilot on this fuel injection system. The pilot's throttle only operates the throttle valve on the engine air supply from the supercharger to the induction pipes. The only thing that the pilot has any influence on is this wire, which is trying to stab me all the time. This is this is the shut-off quick stop lever, which to stop fuel injection is pulled by the pilot, and as he pulls the lever internally, it's simply, if you remember the rack which is moving to vary the fuel amount of fuel injected, it moves that right to the zero position because there's a spring-loaded link in the arm to it, so that it can be under force, can be pushed back, and that turns all these elements to zero output, although they're still going up and down, but zero output, and the engine stops. So that is effectively the only pilot input, is to stop the engine through pulling the quick stop to shut. You could of course turn off the magnetos, but that leaves a lot of charged cylinders in the engine, which isn't good, with fuel in there which you don't want. Turn the propeller and it fires. This method of shutting off the fuel means that it stops without any fuel vapour in the cylinders. You could also turn off the fuel at the fire or the filter cocks, fire cut-off cocks, fuel cocks, and that will stop the engine after 30 seconds or so running, but this system does it by just pulling the lever, injection ceases, cylinders stop firing, engine stops. I'm fortunate to have been able to learn a great deal through the translations that have been done, but their availability in English isn't widespread to my knowledge anyway. You really have to try hard to find these details about the German engines in translated form. So it is my intention to go forward with the translated engine manual and the Messerschmitt 109G flying handbook for publication, possibly in self-published. I think this is the self-publicised bit, but self-published form. Just depends on how it comes together, but I'll be very pleased to be able to get that information out more widely available, because firstly a lot of effort's been put into the translation, and it's very very helpful to be able to read in English if you've not got a decent understanding of German. And you can obtain most of the documents in German, copied German format, but you don't really get the understanding of the systems, I don't think, unless you can get it in a language which is very comprehensible to you. So that is an aim that I've got at the moment.
So perhaps later this year or early next year, people might be able to look forward to that. Yeah,
I've got the problem of putting it all together and making it in a form that's worthy, I think, is the problem. And I'm looking forward to get progress this year, so I'll keep you informed how that goes.
Okay, well, thank you very much for spending so much of your time to talk about all these components and your experiences with the Black 6 aircraft. So just thank you for giving us so much of your time today, Chris.
Yeah, and thank you. And I just say my overriding thanks and my experience with the Black 6 and what I've learnt from it goes down to Russ Snadden and his fantastic project that he was so crazy to start in 1972.